Welcome! My name is Hans, and in this video we are going to cover the topic of outlier analysis. Therefore, we are going to talk about the basic definitions, how to do an outlier analysis and their methods for it. We will focus on the statistical methods, showing an example of how to apply it. This is going to be very useful in the data preprocessing process. This is because the outliers and noise are always in our data. It is not common to have a dataset without outliers. So this might be very important for you in order to work with these outliers, and instead of affecting your process, you might want to create a new point of view from your outliers. Now that you know what is going to be this video about, let's start with some background about what we are going to be looking for. In order to begin with, first we need to know what an outlier is. Hence, an outlier in data mining can be defined as pattern which is dissimilar with respect to the rest of the patterns, or it can also be defined as a data object that deviates significantly from the rest of the objects, as if it was generated by a different mechanism which at the end doesn't have the general behavior or model of the dataset. Additionally, an outlier is usually referred as abnormal data, and at this point you know what is an outlier, but there is a fair confusion between outliers and noisy data. Noise is a random error or variance in a measured variable. In short, noise is not interesting in data analysis, including outlier detection. Therefore, noise should be removed before outlier detection. Thus, for outlier detection, explaining and justifying why an outlier is not a noise data is so important. That is why you need to make some assumptions on the rest of the data and showing that the outliers violate those assumptions. So, knowing what an outlier is, the next part is to know the different types of outliers, because even though identifying the outliers is so important, knowing their type or types is more important for applying the different methods of classifications. Hence, the three most important are global outliers, contextual outliers, and collective outliers. So let's talk about global outliers. Global outliers are registers that significantly deviate from the rest of the dataset. They are also called point anomalies. One example would be a fraudulent bank transaction. To detect global outliers, a critical issue is to find an appropriate measurement of deviation with respect to the application in question. Let's talk about contextual outliers. Contextual outliers are registers that are significantly deviates of a specific context of the object. For example, a register of temperature of 40 centigrade degrees in Merida will not be an outlier because in Merida that is a normal temperature. However, in Mexico City will be an outlier because that temperature is not common there. They are also called conditional outliers due to their dependence on the context. And the contextual outliers have two attributes, which are the contextual and the behavioral. Contextual define the object's context. In the last example, its contextual attribute is the location. Behavioral define the object's characteristics and are used to evaluate whether the object is an outlier in the context to which it belongs. In the last example, the behavioral attributes may be the temperature, humidity, and pressure. The next are the collective outliers. Given a dataset, a subset of data objects forms a collective outlier if the objects as a whole deviate significantly from the entire dataset. Importantly, individual data objects may not be outliers. For example, in Bimbo, that is a transitional. If one delivers gets late, is not an outlier. Nevertheless, if 100 or more delivers get late, as a whole is an outlier. In short, the datasets can have different types of outliers. Actually, it is common that outlier belongs to various types, so identify them is so important. But there are some challenges of outlier detection. So, we can think that identifying outliers, knowing the scene until here is easy. However, the real world can be hell. Therefore, the following is to see those challenges, prepare yourself for the reality. So, let's see how to modeling normal objects and outliers in an effective way. Making a model that integrates normal objects and outliers is hard, if not impossible, because this is partly because it's hard to enumerate all possible normal behaviors in an application. To detect an outlier depends on the dataset. For example, in medicine, if there is a small deviation in the tumor size, could be an outlier, but for selling of an enterprise such Apple, there has to be a large deviation to be considered an outlier. Since outliers are so different from noisy, low data quality and the presence of noise bring a huge challenge to outlier detection. They can distort the data, blurring the distinction between normal objects and outliers. Moreover, noisy and missing data may hide outliers and reduce the effectiveness of outlier detection. And it's important to have some understandability. There are cases where you not only want to detect outlier, but also why those objects are outliers. Meeting the requirements for understandability, an outlier detection method has to provide some justification for the detection. So, after getting the basic knowledge of outliers, we can define outlier analysis, which are various kinds of techniques used in datasets. This consists of the process of finding data objects with behaviors that are very different from expectation and are called outliers or anomalies. So, we have some method outlier classifications that we can put in practice. Here, we presented two different ways to categorize the outlier detection methods. First, we categorize it according to whether the sample of data for analysis is given with the main expert provided level, which can be used to build an outlier detection model. The second, methods are divided into groups according to their assumptions regarding normal object versus outliers. If we receive expert-labeled examples of normal and/or outlier objects, they can be used to build outlier detection models. The methods used can be divided into supervised methods, semi-supervised methods, and unsupervised methods. Let's talk about the supervised methods. These methods model the data normality and abnormality. The sample of underlying data is examined and labeled by expert to the outlier detection can be modeled as a classification problem. Even if many classification methods can be applied, challenge to supervised outlier detection includes some of the following. Sometimes the two classes are imbalanced. This means the population of outliers is typically much smaller than that of normal objects. Due to the small population of outliers in data, the sample data examined by expert and used in training may not even sufficiently represent the outlier distribution. The lack of outlier samples can limit the capability of classifiers built as such. To tackle this problem, some methods make up artificial outliers. In many outlier detection applications, catching as many outliers as possible is far more important than not mislabeling normal objects as outliers. Consequently, when a classification method is used for supervised outlier detection, it has to be interpreted appropriately so as to consider the applicable interest on recall. In summary, supervised methods of outlier detection must be careful in how they train and how they interpret classification rates, due to the fact that outliers are rare in comparison to other data samples. So, we already know what are the supervised methods about. But what about the unsupervised methods? There are some application scenarios where objects labeled as normal or outlier are not available. In this case, an unsupervised learning method has to be used. Unsupervised outlier detection methods make an implicit assumption. The normal objects are somewhat clustered. What this means is that unsupervised outlier detection methods expects that normal objects follow a pattern far more frequently than outliers. They can form multiple groups, where each group has distinct features. However, an outlier is expected to occur far away in feature space from any of those groups of normal objects. Unsupervised methods cannot detect such outliers effectively. In some applications, normal objects are diversely distributed, and many such objects do not follow strong patterns. In such scenarios, unsupervised methods may have a high false positive rate. They may mislabel many normal objects as outliers and let many actual outliers go undetected due to the high similarity. Modeling outliers using supervised methods may be far more effective. And we already know about the unsupervised, but what about the semi-supervised methods? In many applications, although obtaining some labeled example is feasible, the number of such labeled examples is often small. We may encounter cases where only a small set of normal and/or outlier objects are labeled, but most of the data are unlabeled. Semi-supervised outlier detection methods were developed to tackle such cases. Semi-supervised outlier detection methods can be regarded as applications of semi-supervised learning methods. For example, when some labeled normal objects are available, we can use them together with unlabeled objects that are close by to train a model for normal objects. The model of normal objects then can be used to detect outliers. Those objects not fitting the model of normal objects are classified as outliers. If only some labeled outliers are available, semi-supervised outlier detection is kind of trickier. A small number of labeled outliers are unlikely to represent all the possible outliers. Therefore, building a model for outliers based on only a few labeled outliers is unlikely to be effective. To improve the quality of outlier detection, we can get help from models for normal objects learned from unsupervised methods. So we already know that outlier detection methods make assumptions about outliers versus the rest of data. According to these assumptions made, we can categorize outlier detection methods into three types: statistical methods, proximity-based methods, and clustering-based methods. In this case, we are going to see the statistical method. So, now that we know the most important definitions to understand the outliers and the noise, we will get into some methods that are going to be very useful in our way to get a better comprehension of our data. Basically, there are two great divisions that we can make when we are talking about the statistical method, which are parametric and non-parametric. In a moment, I will be explaining them deeply. In this method, we will be assuming, or we may want to see the distribution of our data, because that is the key for this method, to fit the behavior of our data with a statistical model. By having a template of the behavior of the data, we can start to work with our numbers, with more precise algorithms and formulas in order to get the areas of low probability. By taking advantage of these distributions, we will be applying the two methods that I mentioned before. To start with the statistical method, I will be explaining you the parametric method. In this method, we will be sure, or at least we will have a mathematical support of any inference that we might be doing about the data. This is because we will have some parameters that we can use as parameters to compute the outlier according to some specific criteria and rules that exist. At this time, we can talk about the data that is going to be used as a parameter for a normal distribution. We will be applying this parameter and it will drop a probability of the event. Now that we have the probability, we can decide if it is an outlier or not. But who can have know if it is an outlier? Well, it's very simple. If the probability is small, we can expect that it's an outlier. The values that are normals appear in the regions where the probability to be that value is high. Now, let's talk about the non-parametric method. In the non-parametric method, we don't really take a deeper look at the data, because you don't really have to make a lot of assumptions. That is why it has much more versatility with different distributions. The most common non-parametric method is the histogram, but the problem with is that choosing the bins for the visualization is going to be the most difficult part. This because you can have neither less nor more, because that will lead you to a false positive or to a false negative. This is a visualization method that is why it's easier and also not very exact. However, there is a solution for the bins problem, and that solution leads us to the kernel density estimate, which is going to be the perfect method if we want to apply a non-parametric method. In the kernel density estimate, the graph is going to make an operation such as putting blocks over blocks. It is repeated, like putting an Instagram with a low quality of bins, but instead of missing that information, putting another block over the repeated block, and so on. So in that way, you won't have problems with the selection of our bins, and you will be much more sure that you're not getting false positive or false negative. But now that you know all the theory, let's do something much funnier. Let's see how these methods will work. So we have to take in account the univariate and multivariate methods. I need to talk a bit about the detection of extreme data in more than one dimension. That will be the multivariate data. As long as the other ones are working with no so fancy statistical analysis, the multivariate is going to be breaking that paradigm. With these methods, we are not only going to be getting a statistical or probabilistic approach, but also a geometric approach. This is in the case of the deep-based method. In this method, we are going to have n numbers of values which are going to be located in our graph, but we are going to start to put them out of the graph. While we are putting them out of the graph, we will be assigning them a deep, which is going to be the parameter to later use. What we are going to do is that we will start to match the points with the depth that assigned to them, and as the result we will have different levels in the data. The dimensions that we are working with are going to be the key in order to see that we will get much more points in the corner of the graph than in the center. Another way of removing outlier is using the standard deviation. This method, we're computing the mean and the standard deviation of our data. After that, we only need to follow the next rule. If x value is upper than the value of the mean, let's 2 times standard deviation value. Or if x value is lower than the value of the mean, plus 2 times standard deviation value. But besides this method, there exists the interquartile range method, which consists to get the IQR, and this also follows the next criteria. If x value is super than quartile 3 plus IQR, or if x value is lower than quartile 1 less IQR, is considered outlier. And we have to take in account that IQR is obtained from quartile 3 less quartile 1 and the multiplication by 1.5 or 3 in extreme cases. Another method is the t-value test. This method works in a similar way to the z-score, but we need to take in account that this is used for a small number of samples. First, the mean and the standard deviation of the sample are estimated. This is then used to compute the t-value of each data point directly from the sample. The t-value is computed in an identical way as the z-value. The tail probability of each data point is computed from the cumulative density function of the t-distribution, with n less 1 degrees of freedom. As in the case of the normal distribution, standardized tables are available for this purpose. From a practical perspective, if more than 1,000 samples are available, then the t-distribution is so close to the normal distribution that it is possible to use the normal distribution as a very good approximation. Furthermore, there are more methods as probabilistic tail inequalities, sum of squares of deviation, angle-based, and the Malahanovis methods, which are more exactly method but at the same time a little more complicated that in this case we are not going to explain. And it's time to see the most important algorithms. In this procedure we calculate the z-score for each observation. Any z-score greater than 3 or less than -3 is considered to be an outlier. This rule of thumb is based on the empirical rule. From this rule we see that almost all the data should be within the 3 standard deviation from the mean. I'm referring that 99.7% of data. By calculating the z-score we are standardizing the observation, meaning the standard deviation is now 1. Thus, from the empirical rule we expect 99.7% of the z-scores to be within -3 and 3. But, well, how will you represent this? Or what will be the outcome of this? Easy. We are aiming to get a normal distribution where we want the mean and the standard deviation in 0 and 1 respectively. This is very useful because with these transformations we can either use the normal distributions to get our outliers by finding the points that are far away from 0, or we can continue with any other method. But in my opinion, by finding the points away from 0 is more than enough to start to classify. It is important to mention that as long as it is very useful to move from one point to another, and you can also get outliers to form it, it is the most used method. So, in order to see how z-score works, let's going to see an example made by my team. So, we're going to use a dataset from Google, where we have the price of hotels given by Airbnb. Therefore, we will use the data that belong to Manhattan and private rooms. The dataset have been cleaned for us to use it here. And first of all, you can see the distributions right now. As we can see, the distributions are not so similar to the normal distributions, but the z-scores, contrary to what you think, it is not only for normal distributions. So first we need to get the mean and the standard deviation, since we are working using pandas, using mean and STD is enough. By doing this, we get that the mean price and its standard deviation are $128 and 234.66 respectively. So what do we need to do now? We need to get the z-scores for each register of the dataset, applying the formula. What does this mean? As you can see, U is the data of the register, X is the arithmetic mean, and theta the standard deviation. So we apply this formula and we are going to get values close to 0, but we need to establish the thresholds, and since we are using z-score, the thresholds are -3 and 3. By doing this, we can get that there is 43 outliers that is shown below. As we can see, the outliers are expensive price. By doing this, we can have an idea of why those hotels are expensive. Reading their descriptions and knowing this, we can decide if we delete them or still use it for the rest of the analysis. But remember, the outliers were locked to respect the price because it is the record we want to analyze. So applying z-score depends on what you are analyzing, and there is the risk. For using this method, you really need to know where your analysis is focused on. In conclusion, now that we have finished with the examples and the coding, what do you think? Was it easy to learn? Let's make a quick review of what we did. First, we made quick explanation about the outliers and the difference between noise and an outlier. Then we define the two types of outliers and its properties. By doing this, we had a nice point of view about an outlier. Then we show you the classification of the outliers, which led us directly to the methods of outlier detection. And we made a quick explanation of a couple of these methods, how they are supposed to work, and the transformation that they do in order to detect an outlier, or at least to have a better visualization of them. Finally, we used a couple of examples to show you the ones we consider are the most useful and also the most important. It is important to know all these tools for further analysis and to understand that not all data is going to have the same behavior. There are always going to be different distributions, a greater quantity of outliers. Besides, it is difficult to get a dataset without outliers. So next time, instead of complaining about the outliers, remember this lecture and use them in your favor. Thank you for watching this video.